I have a correction to make because the Weil tensor is invariant in all dimensions. The action is invariant only in 4 dimensions. That in 4 dimensions only, the action, which is called Weil action, is invariant. The invariance of the Weil action So the Weil tensor is invariant in all dimensions. The Weil action is invariant only in 4 dimensions. Let's work out the Weil action and see what combination of the 3 invariants it amounts to. And to do that, we would have to square the Weil tensor. That's too long. It's much easier to square the Riemann tensor. And we write the Riemann tensor as Weil minus that. Why is it easier? Because when we square Weil plus G's, we will get many traces of Weil, which is 0, contracting Weil and G. And if instead we square that, well, it will be harder. So let me write that formula. I invert it actually, so Riemann, and I will specify n equal to 4 dimensions only. We do this. So Riemann is equal to Weil minus 1/2. Well, we'll have to come back here because there are many indices to take care of. So Riemann is equal to Weil minus 1/2 R mu sigma G nu rho minus R nu sigma G mu rho minus R mu rho G nu sigma plus R nu rho G mu sigma. And then we have minus 1 divided by 3 times 2 with minus 1/6 mu rho nu sigma. R G mu rho G nu sigma minus G mu sigma G nu rho. The square of that. we will write it simply like that. That is the square of the Weil tensor. So we square the first, plus the square of the other thing. So we first square the second thing, and second square then we square the third one, and then we will do the double products, which will be a little bit easier because of the traces. So let's just square this thing. Square of that is Ricci squared times the square of g. What is the square of g? That's 4. And that you have 4 times. So now we are squaring this bracket. And first we square each term, and then we do the double products. For example, this times this, that's minus 2 r mu sigma g nu rho r nu sigma g mu rho. That's Ricci squared again. These two again. So why 2 here? Sorry. Because it's a double product, yes. So one double product, these two gives minus 2 Ricci squared. This one here gives again minus 2 Ricci squared. Then you have this times this, which gives r squared plus 2 double product r squared, because you see r mu sigma g mu sigma r nu rho g nu rho. Okay, so we have evaluated the double products between the first one and all the other ones. The other ones will be a repetition of this, because so for example this one, oh yes, this one we will have to compute the product of those two. So that is minus minus plus 2 r squared. So we have another contribution like that. Then you have the double product of these two, and then that is a Ricci squared. Finally, you have the double product of the last two, and that is again a Ricci squared, minus 2. So this is the square of the second one. The square of the third one is 1 divided by 36r. And you have the square of this, which is 4 times 4, 16. The square of the second, which is again 16. And then minus 2, the double product, you have g mu rho, g nu sigma, g sigma nu, g nu rho is the trace of g mu nu, so that's 4. Fine. Let's compute now the double product. Weil times this, that's 0. Because there is always a g mu nu that contracts a pairs of indices. Weil times that, that's also 0 because there is always a g mu nu. So it is just sufficient to compute the double product of the middle term with the third term. So that is a minus 2, a plus 2 because of the double product, minus 1/6 and minus 1/2 are the coefficients. R is a coefficient also, and then it's sufficient to multiply g mu rho g nu sigma minus g mu sigma g nu rho times that. But since by anti-symmetry it's sufficient to multiply by 2 and just contract with the first. Okay, so we contract with the first, G mu rho, G nu sigma. The first case we get R. In the second case we get G mu rho minus 4R. The third case, G mu rho G nu sigma minus 4R. And in the fourth case, plus R. And that's it. So Riemann squared is Weil squared. Then there is a Ricci squared multiplied by what? 4 times 4, 16, minus 2 times 4, 8, which is 8 divided by 4, 2. That's correct. R squared. Here we have 2 times 2 divided by 4, 1. And here we have 32 minus 8, 24. So we had 1. 24 divided by 36. That's 2/3. And yes, then there is the last one. Okay, the last one is complicated, so let me write 1 plus 2/3. The last one. So there is a 2. Let me use another color. 2 goes away with 2 plus minus. Here we have minus 4, minus 4, minus 8. Minus 4, minus 4, plus 2, minus 6, which goes away with this. And so we have minus 2R squared. Minus 2. Result, W squared plus 2 Ricci squared minus 1/3 R squared, which is correct. So you find the following thing. We turn it around because we want W squared. That is Riemann squared minus 2 Ricci squared plus 1/3 R squared. So we move these to the other side. Minus 2 Ricci squared minus 1/3 R squared. Minus 1 plus 1/3. It was minus there, plus 1/3. Okay, so those three invariants make in these two interesting combinations either the Weil invariant, the conformal invariant action, or the Euler characteristics, which is a total derivative. But in the end, we remain always with two independent invariants. I will complete this argument with a few properties that from time to time might happen to be useful, depending on what you will do with your research. Another property is that in 3 dimensions, the Weil tensor is identically 0. What does that mean? Well, this is a fact. It means that basically in 3 dimensions, the Riemann tensor is not independent. It's just a combination of the Ricci tensor. So in particular, when you have your Einstein equations that tells you that the Ricci tensor is something in terms of matter, you already know everything in 3 dimensions. The theory is solved. You don't have to go from Ricci to Riemann, which is the difficult part, to solve the Einstein equations. You just have, so for example, r mu nu minus 1 half g mu nu r. We will write, not today, tomorrow maybe, the complete equations with the stress tensor of the matter sector. In 3 dimensions, the equations tell you that Riemann is equal to Ricci, and Ricci is equal to matter, so Riemann is equal to matter, and you can already jump to that. If d is greater than 3, in every dimension is greater than 3, and the Weil tensor vanishes, so in d equals 3 this is meaningless, but in d greater than 3, if the Weil tensor vanishes, then the metric is locally, which means chart by chart. So this is not a global property, but it is interesting time to time, conformally flat. Which means that there exists locally exists a sort of scalar such that the metric is conformally flat, is flat up to a conformal transformation. That is what it means. Very simple metric, just a flat space metric up to a conformal factor, which is this E2 or something. In d equals 3, there is an analogous property that, however, requires us to introduce couple of new notions, which you will meet very rarely, but you might meet them. Let us introduce a Codazzi tensor. Any tensor T mu nu, let's call it tau mu nu, something curly T mu nu, because T mu nu would be the stress tensor. That is symmetric. And such that this property holds which in vector you can also write it with the language of differential geometry. on vector fields. So it's a map from the product of the space of smooth vector fields with itself, a couple of vector fields, into a function on the manifold, such that this holds. Then there is another tensor, Schouten tensor, which is P mu is defined this way. N is T, the dimension, minus R divided by 2 m minus 1 g mu. Schouten tensor is to some extent useful because you can write the Riemann tensor more simply in terms of the Weil tensor and the Schouten tensor instead of listing all the subtractions of traces. P mu. And then the last one is a Cotton tensor, which is a tensor with 3 indices, and that is defined in terms of the Schouten tensor, del mu p nu rho minus del nu p mu rho. What is this useful for? It's useful to state the theorem that generalizes this one in 3 dimensions. So when is a metric locally conformally flat, which means of this form, in 3 dimensions, not when the Weil tensor vanishes, because it always vanishes. So you could say, so all metrics have this form. No, that's not true in 3 dimensions. That's the only exception. And the property is in 3 dimensions. A metric is locally conformally flat if and only if the Schouten tensor there is a C front. Schouten tensor is a Codazzi tensor. Which means we will see that the Cotton tensor vanishes identically. So what does it mean? What is it? When the Schouten tensor is a Codazzi tensor. Schouten tensor is a Codazzi tensor means that the Schouten tensor must satisfy that thing with P instead of curly T. So that means this means that the Schouten tensor is a Codazzi tensor, but then it means that the Cotton tensor is 0. So the right tensor that vanishes identically to identify locally conformally flat matrix in 3 dimensions is the Cotton tensor, which plays in some sense the role of the Weil tensor. I didn't take notes about how the Cotton tensor transforms under Weil transformations, but I suspect that it transforms nicely. But I don't have it here, so I cannot tell you about that. So we'll leave it there. Good. At last, we get to the Hilbert action. And we will start with the Palatini formalism, which means the first order formalism. That's what Palatini means, formalism. But instead of using the spin connection and the field bank, which is what we did so far, we use the metric, which you should have already seen somewhere. So that means that we treat G mu nu and the Christoffel symbols as independent fields. That's first order formalism. Okay. We will have also to specify which assumptions we make. Now the assumption we make is we cannot assume both torsion vanishing and G mu nu being covariantly constant, that is to say metric compatibility. Because if both are assumed, then these are the Levi-Civita connection. This is the Levi-Civita connection, so they cannot be treated as independent fields. Now, normally here, in the previous case with other action, Palatini action in the field by formalism, we assumed metric compatibility and we derived the torsionless condition. Here we assume that gamma is torsionless and we derive the metric compatibility. Now, last year, some of you understood the exercise wrong and proved that the other thing can also be done here. So both work, apparently. So if you want, you can do that. So we assume if we assume that the torsion vanishes, which means that gamma is symmetric, then the gamma field equation implies metric compatibility. Which means that the metric tensor is covariantly constant, and vice versa, apparently. So here we will only do the first, and actually we will not even complete it because I assume that you should already have seen it in general relativity or something. So, but we will go through the main steps and see what happens, and then the little exercise you will have to do, which I think will be the last exercise of this course. So we assume this, which means that that's simpler because we do not have to pay attention to the order of those two indices. Otherwise we risk to make many mistakes, because normally that's what is assumed, and otherwise we have to be very, very careful. So the action is a functional of G and gamma. Okay, of G and gamma. And it is the integral of square root of minus G times R, where R is G mu nu, the inverse metric tensor, times R mu nu. But what is R mu nu? Let us recall how the Ricci tensor is written, and actually we start from the Riemann tensor, which we have derived long ago. In all approaches. The Riemann tensor only knows about the Christoffel symbols, and the same about the Ricci tensor. So Ricci tensor is just a function of gamma, not of G mu nu. G mu nu is only here and here. There is no G mu nu inside R mu nu. Partial sigma gamma nu rho mu plus gamma alpha rho alpha sigma nu minus gamma rho nu alpha gamma sigma alpha mu. And so the Ricci tensor, set mu equal rho, you do not need to use the metric tensor to contract those two indices. Okay. So that's the action. You can now study the variation of the action with respect to g mu nu, which gives the Einstein equations, and g mu nu stays here only. You do not touch gamma. Then if you want, you can study the variation of S with respect to gamma, which acts only inside there, and that will give the metric compatibility. So it's convenient to study the variation of the action instead of with respect to g mu nu with upper indices, because here we have g mu nu with upper indices, so that will make it very easy. And what is the variation of the determinant of a matrix? The variation of the determinant is something like this. The determinant itself times the minor times the variation of the element. There is a minor times the determinant, that is a minor. But since we want to rephrase it as we want delta of g with upper indices, that's minus g alpha beta, or g mu nu if you want, delta g mu nu with upper indices. Okay, that's it. The variation of the square root of minus g is 1 divided by 2 square root of minus g times the variation of minus g. And the variation of minus g is minus g. Variation of g is minus g mu nu delta g mu nu. And so here you have that minus g divided the square root of minus g is the square root of minus g. So you have minus 1 divided by 2 square root of minus g delta g mu nu. So the variation of the action is simple. Delta S is equal to square root of minus g d for x. Now, if you vary this, you have delta g mu nu r mu nu. If you vary inside the square root of minus g, you get delta g mu nu times g mu nu, forgot, minus 1/2 square root of minus g. So square root of minus g is already there. Delta g mu nu is already there. And we remain with minus 1/2 g mu nu, which multiplies r. That's it. Don't need to do anything else. That's the beauty of this formalism, because you don't need to touch gamma. The variation of g with respect to g mu nu inside gamma, when you use the Levi-Civita connection, would be very, very complicated and a useless long work. And then you may want to do the variation with respect to gamma. And we can do that, but first we will not do that, but we can reorder in the action as far as its dependence on gamma is concerned in a convenient way. So let's copy the action and see what we can do. So we just copy the action here. We're not doing anything. We just replace r mu nu with what it is. R mu nu is that, but we have to change the names to all indices. So let's see if we do it. I have to change the name to all indices because instead of nu and sigma we need to, so let me call it this lambda. Alpha can stay alpha. Lambda, 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 lambda. And instead of nu and sigma, that will be mu and nu. Okay. Let's see if we can have it in one line. No, can't. Yes, we can. Okay, so this action, as you see, is quadratic in gamma. So it has a quadratic part and a linear part. Unfortunately, the linear part depends on the derivatives of gamma. But up to a boundary term with a partial integration, we can move these derivatives on the rest. And we will keep the boundary term. It will not affect the field equations, but we will keep it because in the second part we will study the boundary contributions to the action of gravity. And so we will need that. But once we move the covariant, the partial derivative, oh, it's 16. Okay, we have to go. Once we will move the derivative to the left, the action will become algebraic in gamma, no derivatives. So it will be easy to solve it and replace the solution in sight, and that will give the Levi-Civita connection. Okay.